everyone. Welcome to another great session. We're so glad you're joining us today. I'm Erin Gray, the Grants Manager with NunFocus, and I'm really excited for our next session. So I hope if you were ready to uh, learn a little bit about uncertainty, making decisions under uncertainty, you are in the right place. So let's get our umbrellas ready and face that uncertainty. Quan Nguyen, I'm going to let you take over, and we're really excited about your session today.
Thank you so much, Erin. Hello, everyone. I'm Quan Nguyen, and I'll be your speaker for this particular session on Bayesian decision theory and how you can apply it to solve problems where you have to make decisions under uncertainty. And this will be somewhat of a high-level talk where we won't be digging deep into the math, but we'll be talking about the high-level intuition of Bayesian decision theory in the spirit of PyData. So a little bit on who I am. I'm a postdoc at Princeton University, and my research revolves around Bayesian machine learning and decision making under uncertainty. So this is a topic that I quite enjoy talking about, and feel free to connect with me on social media via these links. Okay, so we face uncertainty in many situations in our lives, right? Either um, every morning when we look outside and we see that the skies are cloudy, or when we work as a machine learning engineer and we have to tune the parameters of a model so that we optimize for the test accuracy. Another way that we have to face uncertainty is when we have to design surveys to learn about a particular phenomenon, like political leanings of a particular population that we care about. And the common thread that unites all of these situations is, you guess it, decision making under uncertainty, right? Where there are several factors that make these problems hard. The first one is uncertainty. That is, we don't know what's going to happen in the future. We don't know whether it's going to rain or not. Just by looking in the sky and see that there are some clouds, we don't know how much of an improvement, if there is any improvement in the test accuracy, that a particular hyperparameter combination for our machine learning model will get us. We don't know how each participant will answer a survey question that we'll pose to them. And another factor that makes these problems hard, in addition to uncertainty, is the non-uniformity of the utility and cost, in the sense that we derive different utility, we incur different costs under different scenarios. So, for example, in the weather example, right, rain is usually more cumbersome than sunny weather. You have to bring umbrella or you will get wet. Hyperparameters that yield higher accuracy will obviously be better. Answers in your survey that tell you more about what your participants think will be more valuable than answers that don't really say anything useful. So the balance between not knowing what we have to do and not knowing what we will observe in the future, and the fact that we value some future scenarios more than others is what makes these problems difficult. So the simple example that we'll be looking at to kind of motivate and walk through um, these problems is the rainy weather example that we kind of hinted at before. So imagine, right, that you look outside to your window in the morning and you see that there's some clouds in the sky. So you see that there's a slight chance that it will rain today. So that's the first factor of the problem. Remember, is uncertainty, and the second factor is non-uniform costs that you will get. So in this scenario, right, not bringing an umbrella will get you wet if it does rain in the day, but if it doesn't rain, then bringing an umbrella with you might cause you a minor inconvenience. So the problem becomes, how can you kind of balance between not knowing whether it will rain and um, the slight cost of bringing an umbrella or not bringing an umbrella at all, to risk the fact that you might get wet. So in the theory of Bayesian decision theory, right? What we have to do is to first quantify the specifics, the uncertainty and the cost. Remember, those are the two factors in a decision under uncertainty problem. So in a simple problem like the weather problem that we're facing here, we can quantify the specifics by filling out which this table over here, which we call the probability and associated cost table. So it, in the first row, you will list out all the possible scenarios that you might encounter. And in this example, you have either rain or no rain. And then what you have to do is you have to list out the probability that it will rain and it won't rain, and we'll get into the more specific details about how to kind of get these probabilities out. But let's imagine, for example, that right now we do know that the probability that it will rain is around 30%. And then we also have to specify the cost that we will incur under each scenario, right? So there are two scenarios, rain and no rain, and the two possible actions that you can do is to either bring an umbrella or not bring an umbrella. And in each of these scenarios, so there are 4 different scenarios that you have to specify, rain versus no rain, and bringing an umbrella versus not bringing an umbrella, and you specify the costs in those scenarios. So in this particular example, I'm having here the cost of bringing an umbrella, either whether it will rain or not, it to be 1. So we have to bring an umbrella with us. It will kind of slow us down, make our backpack slightly heavier, so cost is 1. When we don't bring an umbrella, the cost is slightly different. If we do get caught in the rain, we'll incur, we will incur a much higher cost. Here will be 10, but if there's no rain, sunny weather, right, and we don't have to bring an umbrella that will slow us down, then we don't incur any cost at all. So remember the specification of the probability and the cost here is what is the basis of solving a decision making under uncertainty problem, where we kind of make the two factors, right, the two factors that we had before, uncertainty and non-uniform costs or utilities, more concrete. So to solve it, uh, um, yeah, so those are the two factors that we have in any decision under uncertainty problem. So to solve it, right, the goal of the problem, the goal of what we want to do is to come up with a good decision, the decision that will give us the least amount of cost or the highest amount of utility, based on what we know, based on what we think will happen in the future, and with the probabilities that we have specified. So to the objective that I just mentioned can be quantified by the goal of optimizing the expected utility or the expected cost, where here I use the term expected to denote the concept of the expected value, which is the weighted average, weighted by the corresponding probabilities. This concept is a common concept in probability and statistics, and you might have already seen it before, but to make it more concrete, you basically compute again the average of in this example, the average cost of each action that you can take. In this example, we have 2 actions, right? Either bringing an umbrella or not bringing an umbrella. And the average here is weighted by the corresponding probabilities of the possible scenarios. So here I'm computing the weighted average of the cost of bringing an umbrella, which is 1, weighted by the probability of the first scenario, which is 30%. And the other scenario, the cost is still 1, and the probability is 70%. So the weighted average comes out to be 1. For the second action, the expected cost is slightly different. Right now, the cost of not having umbrella in the rain scenario is 10 with probability 0.3, and then the cost in the other scenario is 0 with probability 0.7. So when we calculate out these expected cost values, what we get is the average amount of cost that we will incur based on each individual action that we can take. And what Bayesian decision theory tells you to do is it tells you to optimize for this value, right? Either pick the action that will gives you the least amount of cost or the action that gives you the highest amount of utility. So in this particular scenario, according to the way that we have filled out the probability and cost table, the optimal action, according to Bayesian decision theory, the action that gives you the least amount of expected cost is to bring an umbrella because it gives you the lower expected cost than not bringing an umbrella. So that is the whole idea of Bayesian decision theory, where we maintain a couple of components that help us solve the decision making under uncertainty problem. The first is you need a probabilistic model to model any unknown quantities that you have. This will allow you to reason about the uncertain future that we have to account for while making decisions. So in the language of Bayesian probability, we model unknown quantities using probability distributions, right? For any unknown quantity that we want to model theta, we place a probability distribution P of theta over it to quantify what we know and what we don't know about that unknown quantity. And then we also need to list out all the possible actions that we can take. Um, and then under each action, under each possible scenario, we will specify either the utility or the cost. Um, in many scenarios, utility and cost is just the difference between utility and cost is just a matter of language, right? You can negate the utility to get the cost or vice versa. But in other scenarios, it might be more simple to think about cost in other as opposed to utility than the like the example of bringing an umbrella that we just saw before. But in any case, right, what we have to do is when we kind of have to fill out that um, cost table that we saw, where we specify the cost of utility that we will get under each possible scenario, given the fact that we take a specific action. So this cost and utility function is specified by each action A and each possible scenario theta, each possible value of theta. Okay, and again, right, Bayesian decision theory tells you that you should pick the action that leads to the highest expected utility or the lowest expected cost, optimizing the expected value of your utility function or your cost function. And in math, you usually write it out this way, where you take the expected value of the utility function u with respect to the probability distribution of theta, which is the unknown quantity that you're modeling. So basically, you you're saying that across all the different possible scenarios, across the entire distribution of theta, we want to pick the action A that kind of gives us the highest utility on average. So this rule, right, it balances between the two factors that we talked about. It balances between wanting to optimize for our utility, which is our decision-making objective, but also accounting for our uncertainty by averaging over the different scenarios based on a Bayesian belief about the word, which is quantified by the different probability distributions that we use. Okay, so this is the overall approach of Bayesian decision making. Let's look at more complicated examples to see how you can actually realize this in the real world and what kinds of problems that it will help you solve. Oh, but before that, I should also mention that Bayesian decision theory is highly personalizable in the sense that the two factors that you have, the uncertainty and the non-uniform cost or utility, are all specified by you, the user, right? So it varies. The rule that you derive using Bayesian decision theory depends on your belief about the word and how much you value each possible scenario. So on one hand, the predictive models are probabilistic specific Bayesian which is to say that you can incorporate your own prior knowledge into the model, and that might give you different beliefs about possible scenarios that can happen in the future compared to another user, which means that if you if you have a prior knowledge that is different from another person, then you might have a different estimate of the probability of it being rain, there being rain later in the day, and that might affect your decision making. So let's imagine, unlike what we did before, where we specify the probability of rain being zero point 0.3, now we just have some value p between 0 and 1 and see how that affects our decision making based on Bayesian decision theory, right? So you can imagine that intuitively, if the probability of it raining later is very, very low, like very unlikely that it will rain later, then at one point, right, it might be better not to bring an umbrella at all. So if you were to, plot out the expected cost as a function of the probability of um, there being rain later in the day, then you can see that there's a interesting change in the optimal decision that you have, where if your probability of rain is lower than zero point 0.1, then the optimal action is not to bring an umbrella because the expected cost of that action is lower than the expected cost of bringing an umbrella. But, and this is pretty intuitive, if the probability of rain is sufficiently high, in this case is bigger than 0.1, then the optimal action is to bring an umbrella. Again, I'm trying to make the case that based on what values you put in the probability row, the optimal decision changes. So it's personalized in the sense that it depends on what your belief about the word. In this specific case, your belief about how likely rain is later in the day. The utility and cost is also dependent on your own personal preferences, right? So you can imagine that if you, like me, usually carry a laptop with you when you walk outside, then maybe getting caught in the rain is more catastrophic than incurring just 10 units of cost, right? And if your laptop gets broken or whatever, then it could be even worse. So the optimal action in Bayesian decision theory also depends on the utility and cost that you specify. So like what I was hinting at before, right? If see here the value of getting caught in the rain without an umbrella is much higher than the rest of the cost values, then you can imagine that bringing an umbrella is usually the optimal action. So we can inspect that by kind of plotting out what the optimal action is as a function of not just the probability of rain like we saw before, but also the cost of getting caught in the rain. See over here in the y-axis. And here this heat map is trying to show that as your cost of getting caught in the rain increases from around 1 here to 20, then the optimal action is increasingly um, becoming bringing an umbrella, right? Like bringing an umbrella becomes more and more optimal. When the cost of getting caught in the rain is around 1, then the optimal action is not to bring an umbrella at all. When the cost is around 10, then if the probability of rain is less than 0.1, then you might still get away with not bringing an umbrella. But when the cost is really high, like 20, then only when the probability is very low in this region. Otherwise, you should bring an umbrella with you to kind of account for that very high cost of getting caught in the rain. So overall, right, the point of this slide is to say that the optimal action that you take heavily depends on, first of all, your uncertainty about the world, what will happen with what probability, but also utility and cost that follows your own personal preference. So in this slide, I want to talk a little bit about one particular application of Bayesian decision theory that we saw before in the problem of Bayesian optimization. And in Bayesian optimization, the goal is to optimize for what we call a black box, expensive to evaluate function. Um, and what we want to do, so the goal is we have a function. We don't know the functional formula. We don't know what the formula is, but we can evaluate that function at specific points in the domain. And what we want to do is want to identify the input, the location where the function is at the highest or lowest. So what we want to do is we want to pick out evaluations of that function. We want to pick out specific inputs for that function to sequentially evaluate it to quickly identify the minimum or the maximum. And there are a lot of problems in the real world that can be modeled using Bayesian optimization, right? And we talked a little bit about hyperparameter tuning before, where the motivation behind it is that the cost of training a model is increasing very fast. And this is especially true for large language models, where the training compute time increases exponentially as a function of time. And this motivates the fact that you want to only retrain the model for a low number of times, for only a couple of times. You don't want to do it hundreds or thousands of times, right? Because every time you retrain a model, it might take hours or even days to run, and you have to spend a lot of money on GPUs. And so you don't want to do it for a large number of times. So by taking on this Bayesian optimization approach, where you want to strategically pick out which hyperparameters to model, to train the model with, you can try to optimize the function, in which case it's the test accuracy, as quickly as possible. And in addition to hyperparameter tuning, right, other applications are common too. For example, for scientific discovery like protein or drug design materials discovery, you can imagine a scientist navigating over a very large database of molecules or drugs or materials. And what they want to do is to quickly identify those with an interesting characteristic. But every time they want to study one particular data point, they have to spend a lot of time in the lab to perform experiments. So they only get to pick out a small number of data points to study. Another related application is product recommendation, right? You want to strategically showcase specific products to a user, but every time you recommend a product, right, that might constitute a break in their user experience. They have to be you have to send them an email or show them an ad, and that might bother them a little bit. So you don't want to do it for many times. So you want to still strategically pick out a small number of products to recommend to them. So you can follow this Bayesian optimization framework. So by applying Bayesian decision theory, you can come up with a way to address Bayesian optimization. First, you need a model, right? You need a model to model what you know and what you don't know about the world. That is your uncertainty about the world. And in Bayesian optimization, the common approach is to use what's called a Gaussian process, where each prediction is not just one single number, but an entire normal distribution with a mean and a spread. Here is what you usually see as a visualization of a Gaussian process, where each black X here is an observed data point, right? Where at each prediction, you not only have the mean prediction, which shows you the most probable prediction as the blue line here, you also have the arrow bars, which are the shaded regions over here, that show you how confident you are in these predictions. So in the region where you're close to an observed data point, then your uncertainty will be low, so your error bars will be small. But outside of that, right, your error bars will get bigger and bigger as you move further away from your training data. And what you want to do to implement Bayesian decision theory is to want to specify cost or utility. In this case, we have utility. So one way to do it, right, is when you try to maximize an unknown function, is you can say that our utility is dependent on how much we can improve from the current best. An example that I have over here is 0.8. So if the next evaluation yields a higher test accuracy, this is under the example of hyperparameter tuning again. So I care about test accuracy. So if the next iteration gives me 0.9, then my utility for that scenario is 0.1, which is good. Otherwise, if the utility is not higher than my current best, sorry, the next accuracy is not higher than my current best 0.8, then my utility is 0 because I don't get any further utility for evaluating the next input of the function. So by combining the predictive model and the utility function, we can compute the expected utility of evaluating the function at each specific input point again by taking the average value of the utility function that we have defined so far. Where the goal, according to Bayesian decision theory, right, is to maximize the expected value of the utility function, which again is this improvement function that we define, where f star here is the current best that we have found. And here I'm plotting out that score, that expected value of the improvement score, given the scenario that we have over here, where we see that the score is maximized around this point. So that will be what we do, right? We will pick the point that has the highest utility to pick it as our action. And what's interesting about this problem is that by applying this Bayesian decision theory approach wholesale, we naturally get this interesting behavior that balances between exploitation, where we focus on regions with a large predictive mean like this region, but um, we also balance that against exploration, where we also focus on regions where there is a lot of uncertainty in our prediction, like these regions. So here's an example where we run this Bayesian decision theory policy for Bayesian optimization from scratch, where you see that at the beginning, it kind of spends some initial time exploring the search space, but it quickly narrows down to the good region that contains the actual optimum of the function. Okay, I see that I'm running out of time, so I will quickly talk about another common application of Bayesian decision theory in experimental design, where in this case, you don't want to optimize for a function, but you want to learn about that function. So what you can do is you still have a probabilistic model, you can have a Gaussian processor, you can have another thing. But what you want to do is you want to specify the cost in this scenario, and the cost here can be done with the entropy of the probability distribution. High entropy is a common measure of how uncertain you are about a probabilistic quantity. So high entropy means that you are very uncertain about that quantity, and which means that you have a very high cost for that particular scenario, right? You want to learn as much as possible about quantity, so you don't want to be uncertain about that. Here's an example where we are fitting a probability distribution on the bias of a coin. And what I'm trying to show here is that as the probability distribution becomes narrower and narrower, so our knowledge about the unknown quantity becomes better and better, the uncertainty decreases. So you can use Shannon entropy here as your cost function for experimental design and choose the function evaluations to best minimize your expected uncertainty. And that gives you what people usually call information gain, entropy search. Here's an example that I have used before, where you want to estimate the disease transmission rate tau by measuring how many people that have been infected over time at specific amounts of time. So you strategically picked out time slices to study the model, and by by picking out these terms, right, your belief about what the true tau is becomes narrower and narrower by applying this Bayesian decision theory approach. Okay, so as the last takeaway I want you to have is that Bayesian decision theory, right, is about picking the action that optimizes for the expected utility and cost. And in the umbrella example, we saw a simple example with where we can specify the cost table. In Bayesian optimization, we see that we can use this to optimize for an unknown function. In experimental design, we see that we can use this to learn about an unknown quantity as quickly as possible. But there are many things that can go wrong. You can have misspecified models, misspecified cost and tables, and then there will be computational challenges that uh, that disable you from computing the optimal action that you can get. In the last slide here, there'll be links that you can use to find more resources that will help you explore this idea of Bayesian decision theory, Bayesian decision making under uncertainty in general. And there'll be some free book giveaway that my publisher is doing. So feel free to get in touch if you're interested. And I'm sorry that I'm out of time, Aaron. But thanks so much for your attention, and please reach out if you have any questions.
No, this was wonderful, Quan. Thank you so much. And I just want to let everyone know, just a reminder that you can go to the Discord channel to continue the conversation. I'm sure that Quan will be happy to also put these QR codes and resources there as well. And you can also connect with Quan through the reception area on the conference site too. So thank you so much, Quan. This was wonderful. And the recording of this will be released pretty shortly. So thank you so much for providing this today. Really appreciated it.
All righty. Thanks so much, Aaron. And like Aaron said, I'll pop into the Discord channel and or the other platforms.